Through this talk, I would like to present a recent experimental result that we have obtained in Vienna. And it deals with an experimental investigation of an indefinite causal order. So, to give you an outline of my talk, I will just give you a very short motivation of why it's interesting to study this type of processes. I don't think I need to convince you. And then I will once again present you what is a causally non-order process. Then I will, in this context, I will have to break the trend that was followed so far from my colleagues, and I will have actually to introduce the process matrices. I'm sorry. They left me the dirty job. And then, then afterwards, I will introduce the causal witness, which was the tool that we used to demonstrate this type of that this type of process is causally non-separable. Then I will present you the experiment we have performed to measure this type of witness, the result we have obtained, and then some conclusions. So first of all, the motivation. In 2012, the quantum switch was proposed. And in the same year also, the Oreshkov-Costa-Brunker paper appeared with the formalism of the W's and these causal inequalities. Afterwards, also several other theoretical papers appeared demonstrating the advantages of this type of processes in terms of quantum communication and computation. However, up to that point, nobody yet had demonstrated that this type of processes could be built in a lab. We did it in the University of Vienna through this paper that appeared in 2015. Nonetheless, this was a demonstration which actually was not very broad. Let's say it was demonstrated only for 3 standard deviations, and it was used by means of a kind of a game. We were demonstrating that we were able to obtain a very high probability of success in deciding whether 2 gates which were applied only once were commuting or anti-commuting. Now, the problem for which we only obtained 3 standard deviations was that actually already the probability of success of the standard order case was pretty high. And so due to experimental imperfection, it was not possible to get a very high discrepancy. So what we wanted to do, it was basically to make a broader demonstration of the existence of this type of processes. So, first of all, what do I mean for this type of processes? Causally non-ordered processes. So, during this presentation, I will always consider 2 laboratories, an Alice and a Bob, and I suppose that they are closed inside their laboratory, and the only interaction that they can have with the external world is through the state that they receive as an input and the state that they emit as an output. Now, once again, the quantum switch. So suppose that they will act on the same qubit that I will call target qubit. And, of course, either Alice will act first and then Bob, or vice versa. So suppose that, for example, I will use a control qubit to decide who will act first. So, for example, if the control qubit is 0, then Alice will act first and then Bob. If the control qubit is 1, then Bob will act and then Alice. And, being them a quantum qubit, I can also put the control qubit in a quantum superposition of 0, 1. And so I will also be able to have a quantum superposition of the 2 situations, Alice acted first and Bob acted first. Now, in this type of scenario, let's suppose that Alice and Bob perform a measurement on this target qubit. So, for example, let's suppose a situation where Alice performs a measurement MA, so she chooses between a possible set of measurement, one that we will label as X, and she will get an outcome A. Bob will perform on this input state that we choose as Z, a measurement MB, that we will choose as a Y, and we'll get an outcome B, and then we will perform on it a detection operation D. The probability of getting A, B, and D given X, Y, and Z is given through this formula, where this W is exactly this process matrix. And now the important point here is that this is a product. And so the W does not depend on what Alice performs, on what Bob performs, on what I insert as an input, and also what I perform in the detection operation. So somehow, going back to the situation of before, if we consider this type of scheme, we can consider that the W is basically what is inside this box. So it's the way in which the information is transmitted between the parties. So it's basically the information which is transmitted from the input state to Alice and Bob, and then from Alice to Bob and Bob to Alice, and then finally to the detection stage. Now, the aim of our experiment was to build a process that we believe is causally non-separable and to calculate a causal witness on it and demonstrate that it is actually causally non-separable. So first of all, what do I mean for causally separable and causally non-separable? So a causally separable, a bipartite W that can be written in this form is representing a causally separable process matrix. So basically, it's a classical with a classical probability P, Alice will act before Bob, and with a probability 1 minus P, Bob will act before Alice. Now, the process matrix of the quantum switch, we believe, and we demonstrated, it's causally non-separable. So first of all, how do we write this process matrix? This was the scheme of the quantum switch as I showed you. Now, in our experiment, we decided to measure only on the control qubit. So basically, what our operation was to trace out in the Hilbert space of the control qubit. And so the process matrix of the switch can be written as this ket bra of the vector of the quantum switch, which has this form. So, as I said before, if the control qubit is 0, Alice acts before Bob, and if it's 1, Bob acts before Alice. And what do I mean for Bob acts before Alice and Alice acts before Bob? For example, the vector Alice acts before Bob is this type of vector, where these are double ket in the Choi-Minkowski isomorphism. And so they go from the Hilbert space of the input to the Hilbert space of the input of Alice, output of Alice, input of Bob, output of Bob, overall output. So all in all, this is the form of the W of the quantum switch. Now, the entanglement witness is a tool that we can basically really consider like the analog of the entanglement witness for the case of entanglement. So let's now consider the case of the entanglement. I have a state and I want to decide whether this state is entangled or separable. What will I do? I will measure on the density matrix of this state this entanglement witness. And depending on whether I get a value which this case is above 0 or below 0, I will have demonstrated that my state is entangled or separable. Here it's exactly the same. So this causal witness is defined as an Hermitian operator S, such that if I do the trace of this Hermitian operator over a W of a causally separable process, I will get something which is bigger or equal to 0. And if it was causally non-separable, then it will be below 0. In particular, in our process, we decided to, in our experiment, we decided to define a causal non-separability parameter, which is defined as minus the trace of this trace of the causal witness with the W. And so basically, if we get a value which is above 0, we have demonstrated that our process is causally non-separable. So this brings me to the purpose of our experiment. We wanted to calculate this causal non-separability of the switch. And so we had basically, with this program that was computing the causal witness, we got a list of measurements that we had to perform. For each measurement, we were getting some probabilities. We were multiplying these probabilities for some weights that we were getting with this program. And then we were just summing them up, change the sign, and if we were getting something above 0, we have demonstrated the causal non-separability. Yeah, it was basically we were projecting the control qubit in plus and minus. So the D, it's just... The detection is at the end. But we also, as I will show now, so there is a detection stage at the end, but also Alice and Bob will perform something on this qubit. They could either perform a unitary operation or a measurement operation. Now the fact is, if they would both perform only the unitary operation, they wouldn't get any information out of this operation because, of course, it's a unitary. But if they were performing a measurement operation, then they would get some information. And so basically, this would be kind of a tool also to get information of what is happening inside the quantum switch. So basically, we had, and this is also what we did actually, because as I will show you now, one of them performed a measurement operation and the other performed a unitary operation. And so this was something that allowed us to not only obtain the information of what was happening outside at the end of the quantum switch, so in the detection stage, but also inside through this measurement operation that L is performed. So maybe I can go to the scheme and maybe it will be more clear. So this is the experimental scheme. There is a state preparation stage, just some waveplates and a Polaroid and waveplates. And then the beam impinges on a first beam splitter, and then depending on whether it's transmitted or reflected, it will be subjected to the operation of Alice and then Bob, or Bob and then Alice. And then it will be interfered again in a second beam splitter at the end, and this will complete the operation of the switch. Now, as I was saying, either they could perform a unitary operation, which means in our case, since we were implementing the the control qubit in the path degree of freedom and the target qubit in the polarization, a unitary operation would just be a sequence of 3 waveplates. Or otherwise, it could perform a measurement operation. So this was the controversial part, because at the beginning we didn't know how to perform a measurement inside, because we thought, okay, but if we perform the measurement, then we break the interference, and so the quantum switch doesn't happen anymore. So the trick that we found, we thought was, okay, but if we don't get the time information right after the measurement, but we actually keep it up to the end, and we only read it up after also the interference up in the second beam splitter, then we cancel the time information that they would get, and so we don't erase the time information of, like, because we don't want to know if Bob acted first or Bob acted before Alice, otherwise you would destroy the quantum switch, because we believe it's in a quantum superposition. And so we only maintain basically the information in this kind of splitting ratio of the two intensity of the beams entering the PBS, and then we arrived up to the end, and then we performed the measurement only outside the quantum switch. But this measurement inside still gave us some information. Indeed, this was basically the reason for which we were able to get a much broader discrepancy between, like, the distance from the case of causally separable and the case we obtained. So we got basically more standard deviation distance, exactly due to this presence of this measurement here. So, as I was saying, the main result we wanted to obtain from this experiment was calculating these probabilities. Calculating these probabilities, they were multiplied for this alpha, and then sum them up and obtain something above 0. So basically, suppose like I send 100 photons, and then I see how many photons I get out of all these detectors. And from this kind of splitting ratio, I will translate them in probabilities. I will multiply them for these alphas and get the outcome. And the outcome we obtained, so, was basically, as you can see here, it was a list of probabilities that then we just summed them up together and brought to this value. So 0.202 plus minus 0.029. So for 7 standard deviation this time, we demonstrated that we cannot consider our process as a causally separable process. Now, once again, analogously to the case of the entanglement witness, the entanglement witness can be considered as a measurement of the robustness to noise of the entanglement. Also, the causal witness can be considered a measurement of the robustness to noise of the causal non-separability of the setup. So another thing we wanted to do was actually observe this robustness to noise of the setup. So what we did was something quite similar to also what they did in the former experiment to introduce the noise. So we had some slide to introduce a delay of 1 photon with respect to the other impinging the second beam splitter. And this was meaning that, of course, like, you will have a diminution of the visibility of the fringes because they are not time indistinguishable anymore. And so, no? Okay. So we were delaying 1 photon out of the other, and this way we were inserting a dephasing noise. And what we have observed was a situation like this. So this is the theoretical trend, and this is the experimental trend we have obtained. So as you can see, there is a discrepancy between the theoretical trend and the experimental trend, although this is still enough to demonstrate that the process we have implemented is actually causally non-separable, and we are still able to detect the causal non-separability of the setup also when we have a diminution of the visibility of the fringes of roughly 35%. Now, why do I have this shift in the experimental trend with respect to the theoretical one. It's a purely experimental reason, and it's due to the experimental imperfection. In particular, as you can see, like here, there are several points where you have either 2 or 3 beams impinging the wave plates. And so, in principle, we want that, of course, this is, for us, just a unique Alice, and so she would be implementing the same operator in each of these beams. But actually, this is a wave plate. And so it's impinging 2 different points of the wave plate, although they are just slightly distant. What resulted was that probably the operator that was implemented in one point was slightly different from the other point, although they were just distant 1 millimeter. Nonetheless, as you can see from this trend, this error which was introduced was still kind of very, very small, and so we were still able to demonstrate that actually the process we have implemented, it is a causally non-separable process. So, to give you some conclusions, what we have done was an experimental demonstration of the causal non-separability of the quantum switch, and to do so and to obtain a broader demonstration, we have performed for the first time a quantum switch with a measurement channel inside. And what we want to do next, most probably we will, now we demonstrated that this type of processes do exist and can be built in a lab, and so we want also to demonstrate that these type of advantages that we can get in terms of quantum communication and quantum commutation can also be achieved and implemented. So with this, I would like to thank you for your attention.